In this problem, we're going to use a technique called node voltage analysis to solve a complex circuit that can't be simplified using simple parallel and series circuit and resistor simplification rules. And node voltage analysis is really an application of Kirchhoff's current law. We're going to use Kirchhoff's current law to basically to simplify this circuit to create a set of equations that we can use to solve it. So here are the steps here. We're just going to go through it step by step. And step one is to label all of the nodes on our circuit. Now, a node is really just a conductor. It's a conductor in which there's going to be circuit elements on either side. So I'm going to label my nodes with yellow highlighter. Here's a node here. It's between these two elements. Here's a node here, and it also even goes down to here. Here's a node here. And there's also a node down here, but it extends all the way down this wire. This whole bottom conductor is a single node, and it's at the same electric potential. Let's label our nodes A, B, C, and D. This bottom one is going to be node A. I'm going to label this top one node B. We're going to call this node C and node D. So we have all of our nodes. We have them all labeled. Next up, we need to choose a reference node and label it ground. And ground just means 0 volts. Now the trick here is we're going to be looking at these nodes and figuring out the potential difference between them. But just like potential energy, it's only a change in potential energy that matters. So we can choose an arbitrary position to be 0 potential energy. And it's the same for electric potential. We can choose an arbitrary position to be 0 potential, and we call that ground. And we label our ground with this sign down here. I'm going to choose node A to be ground because it's connected to 1, 2, 3 elements. And it's also connected to the resistor that we're trying to find. We're actually going to be trying to find the current and the voltage across that 5 ohm resistor. So this is going to be our ground. I'm going to just label it blue to match it up with our instructions. And the voltage of the ground is it's set to be 0 volts. So V of A, or VA, is equal to 0 volts. That's the potential at node A of this entire thing. Okay, so we need to then label currents along each path, I1, I2, etc. Since we only have 2 nodes that have more than 3 paths attached, node A and node B, I'm only going to label the currents. I'm only going to label the currents going into node B. So I'm going to label this I1. I'm going to label this I2, and I'm going to label this current I3. And I chose them all going into node B just really for no particular reason, just because. But they're all going to be going in like that. Let's highlight them just so we're clear that these are our 3 currents. And this I3 is, of course, the current around this whole loop. This I2 is here, and this I1 is the current around this whole loop. So we have our currents drawn up, and our goal is going to be to find the voltage, or really the potential, at all of these nodes, or at least the nodes that we care about. Really, we only need node B. So what we're going to do is we're going to write down the voltage of all of the nodes that we actually know. Since this is the ground, this is 0 volts. If we go across this EMF source, this voltage source, we have an increase of 10 volts. So I'm going to label the voltage at C equals 10 volts. We can do the same thing over at node D. We start out at 0, we go up 12 volts. So the voltage at D is equal to 12 volts. Now I forgot to write that in the instructions, so I'm going to write that right now. Label potentials for all known nodes. Now once we have that, that's our basic setup. What we have to do next is actually use Kirchhoff's laws to set up a system of equations to solve. And in node voltage analysis, we're going to actually be using the current rule to write out equations at each junction. A junction is just a node that has 3 or more paths coming into it. So that's going to be node B or node A. So let's get that set up. Node A is going to be the easiest, and in fact, I'm going to zoom in a little bit. Node A. Kirchhoff's current rule says current coming in equals current going out, and we're going to use that to find the voltage. But node A, we already know the voltage. So since that's the ground, there is no equation needed. So the other node that we are interested in is node B. Everything else we actually know. Node B is our only unknown here. So let's write out an equation for node B. Node B. And we're just going to use Kirchhoff's current law to sum up the currents here. The sum of the currents in this case, is going to equal the sum of the currents out. And here I have 3 currents in, I1 plus I2 plus I3. And I have none coming out. So that's going to be equal to 0 on the left side. Now what I'm going to do is I'm going to rewrite all of these currents. This is the next step, step 5. I'm going to use Ohm's law to rewrite all these currents in terms of my known quantities and my node voltages. So we know that current is equal to voltage over resistance. So let's look at the voltages here in terms of the node voltages and the resistance. I'm also going to label node B VB for this one. So I'm going to zoom in a little bit. I1 is just equal to, well, I1 is going through this 8 ohm resistor, so the voltage is the potential difference between VB and node C, which is 10 volts. So if we do V over R, we're going to get VB minus 10 volts, all divided by R is equal to 8 ohms. And then I2, we have, well, the potential difference is from node A to node B, and it's 0 to VB, so it's just going to be VB over 5 ohms. And then we do the same thing for I3. I3 goes across this 4 ohm resistor. Our voltage difference is going to be VB minus 12 volts, because that's the potential difference, 12 volts to VB, divided by 4 ohms. And that whole thing is equal to 0. Now most of the rest of this is just going to be algebra, so let's get moving. In order to solve this, we need to find a common denominator. That common denominator is going to be 40, at least that's what I'm going to use. And so we're going to get 5 times VB minus 10 volts over 40 ohms plus 8 VB over 40 ohms plus 10 VB minus 12 volts over 40 ohms is equal to 0. Now that we have a common denominator, we can add these all up and we'll have a common denominator. And we can also simplify. So I'm going to simplify a little. 5 VB minus 50 volts plus 8 VB plus 10 VB minus 120 volts all over 40 ohms is equal to 0. Now I'm going to eliminate that. I'm going to multiply by 40 on both sides to eliminate it. Oop, there's a text message. And we're going to get, we have 5 VB, 8 VB, and 10 VB. That gives us a total of 23 VB. And we have minus 120 and minus 50, so that's going to be minus 100 and 20 and 50 is 170 volts is equal to 0. I multiplied by 40 on both sides to cancel that out. We then get 23 VB is equal to 170 volts, or VB is equal to 170 volts over 20, so let's erase that, 23. And that gives us the voltage of node B, or the potential. 170 over 23 is 7.39 volts. So that's not quite our final answer, but we're pretty close. We're trying to find the current and voltage of the 5 ohm resistor. And we have the voltage at every node, so I'm going to come up here to write out how to find my final answer. So the voltage across the 5 ohm resistor, if we go back to the diagram, is just the potential difference between A and B. So we know it goes from 0 to 7.39. So the voltage across the 5 ohm resistor is just going to be equal to 7.39 volts. If we want to find the current then through our 5 ohm resistor, we can just use Ohm's law. Current is equal to voltage over resistance. So that's going to give us 7.39 volts divided by 5 ohms. And that gives us a final current of 1.48 amps. That is the current through our 5 ohm resistor. So there you have it. There's node voltage analysis. We find the voltage at each node using Kirchhoff's current law. And then we use the potential difference between nodes and Ohm's law to figure out our unknowns. There's an equivalent alternative analysis called loop current analysis, and I'm going to show you that in another video.